So, promise theory. Imagine a world made up of entities. We can call them agents, and these agents experience the world through some sort of a boundary. Let's have a picture. Here we go. These are the agents, kind of cellular entities, and these things are independent. We might call them cognitive agents because they're able to receive signals from one another or emit signals from one another. So they receive input, they process it, they produce output. What goes on inside them is kind of unknown, but we can give them names. So they have identities, A1, A2, A3, and so on, all the way up to some AI, no pun intended. And they are floating around in some world which we don't know too much about. But that world is unimportant for the most part. Everything that happens of interest happens inside the agents. Now, I stumbled across this idea back in the 1990s while developing computer software, actually called software agents, in a software called CF Engine. And what computer science normally talked about was what a computer might do programmatically if you feed it some algorithm. And in that sense, what the computer produces is pretty much deterministic based on the program that you give it. But in reality, most agents that are decoupled from each other, especially in distributed systems, are not deterministic at all. We don't know exactly what they're going to do. They may or may not be able to keep their promises. And so we would like to have a way of describing this scenario and to figure out what is going on. So we start from the assumption that this world is composed of autonomous agents, and they express promises to each other, which you could draw as a kind of an arrow between them. And the arrow has a label on it, which is we call the body of the promise. This body is some signal, like I promised to give a talk about promise theory, and the promises actually come in two kinds. There can be a promise to produce something or to offer, to make an offer, like I'm offering this talk on promise theory. And there can also be a talk. There can also be a promise to receive something. So just because I promise to give you something doesn't mean you have to receive it. And this is the nature of autonomy. So if agents could be commanded and controlled, in detail from the outside, as we tend to believe they can, then you might be able to govern the entire system deterministically. But because they can't, because they are fully autonomous, you can only talk about best effort. So S can make its best effort to produce some output, BS, and R will think about what it can be bothered to listen to. So right now, I'm giving this lecture, and maybe you're talking on your phones or texting or something like that. So you're not listening to 100% of what I say, but you might be listening to 90% or 60% or whatever it is. And so when we talk about the interaction between things, agents have plus promises, which are offers, and minus promises, which are acceptances. And you can picture this, if you like, as what happens when you use a screwdriver. The picture on the right-hand side. The offer by the screwdriver is to have, say, a flat blade, and then the screw top has a receiver promise to accept the flat blade. And if they match, then something can be transacted between them. But if they don't match, then perhaps nothing is, perhaps it simply doesn't work, and the things don't couple at all. So we can write these promises then as arrows between symbols, and in three different ways. At the top, straightforward kind of symbolic structure. In between, it looks like a graph, so some blobs or agents with arrows between them with labels on. And underneath, we can write the promise formally as an algebraic structure. So pi s is the promise to offer from S to R, the plus quantity bs. and pi r minus is the promise to receive by r. Oops, the arrow is going the wrong way there. It should be from r to s, to receive. And the overlap of these two quantities, bs and br, which, let's say, they're just sets, this intersection between the two sets is what is transacted between the two agents. Now there's one other kind of interaction which we can try to make, and this of course is the classical philosophical obligation. In computer science, again, people tend to believe that they could control things by imposing instructions on them so that they were obliged to or compelled to obey. This actually is ineffective in promise theory. We don't believe that this can happen because the agents are causally independent. So the best we can do is we can try to like throw a ball to somebody and hope they catch it, but we can't guarantee that they'll catch it. And similarly, we can't create any kind of control command structure and just throw it at an agent and hope that it will, or know that it will succeed. So impositions and obligations are the traditional way of talking about command and control, but they are ineffective ways of communicating in promise theory. There's one more detail which again goes back to this autonomy, and that is an assessment. If agents are fully autonomous, just because I send S and you accept R and then there's some S intersect R thing going between us, doesn't mean that R believes that the promise has been kept, that it was offered something by S but it hasn't received what it was promised. And that assessment every agent has to make on its own. It can't be, again, it can't be forced, it can't be imposed. Agents may have very different points of view as to what they believe is a kept promise. And they can assess this with some function, we usually call it alpha, and it's labeled with an R to show that it's the receiver making the assessment based on the promise from the sender. The assessment can be made in units of different kinds, so maybe simple yes or no, kept, promise not kept, and so on. Or it could be, yes, I'm happy about the outcome, or I'm ecstatic, or I'm angry, or I'm red, green, black, or whatever it is. That doesn't matter. So the key to all of this is that this world of agents is producing voluntary cooperation. It's not forced, compelled obligation. It's every agent for itself doing its best, trying best effort. Now, if we draw all of this out, and all of the agents and all of the promises between them, it forms kind of a half graph. Each plus promise is an arrow, each minus promise is an arrow. And in order for anything to transact between them, we need the plus and the minus complementary promises to join them up. So when we take the adjacency matrix of this graph, filling in the lines with the promises, nothing happens. But if we multiply the two parts together, the forwards or the plus and the minus promises together, we create a regular graph, a directed graph. So notice that even though the arrows go in both directions, the promise flow is only going in one direction because it's being sent and received with different roles. And this is not ordinary matrix multiplication, but Hadamard multiplication, in which we multiply the elements row by row or element by element. So does all of this mean that promise theory is really just a route to get to graph theory and then you're done? But no, that's not the case, because the graph theory typically is undirected. It's typically about the connections between links rather than what's going on inside the agents. Again, come back to this point about autonomy. It's really about the autonomous nature of the agents and how that affects the way they interact. The fact that they form a graph is just a coincidence. but we may use it in the future. Now, the question of time is important. If an agent makes a promise, is this a one-off thing, like a simple one-shot transaction, or does the promise sustain a kind of continuous steady state of activity? And if so, then how does the receiver receive it? Now, there is a theorem in Shannon's information theory that when an agent produces a signal, it sends the signal at a certain rate. The receiver has to sample that channel at twice the frequency of the sender in order to be absolutely certain to capture the whole signal. Now that means that if every agent next to every other agent has to be sampling twice as fast as the sender, this means eventually everybody has to be working at an infinite rate, which is impossible. So that means that every agent interaction, whether it's one-off or continuous steady state, has a rate which is measured by time set by the sampling rate. And that means that the agents are operating in a non-deterministic way because they only have a finite probability of capturing the signal. We don't know exactly what that probability is, but that's an important thing to keep in mind. Not least because when we reach sort of the human level of promises, we tend to say that we need to trust we need to trust agents in order to rely on their promises. So if we want a reliable system, a trustworthy system, then we need to be able to talk about the rate at which time runs, the sampling rate of these agents locally. Now, let me go to the next slide here. This issue of trust and sampling brings us to energy, because in physics, energy is the history, if you will, the accounting parameter that sums up all of the transactions that have been made over time. Energy and time are complementary variables. So in order to speak about time and sampling, we also need to be able to speak about energy. And the way that energy manifests at the human level, the higher level of promises, is trust. Trust is about measuring. So trust actually has two components. There is the potential for trusting, the potential for assessing an agent as trustworthy. So we sort of believe that it will keep its promises to some extent. And then there's the kinetic trust, which we sample repeatedly to make sure that the promise has been kept. Are we there yet? Are we there yet? And so trust is really very much like energy. It has two parts, a potential part and a kinetic part. Now, so trust really has to work in exactly the same way as it works in mechanics, because it's basically a dimensional argument. On this slide, it shows you how you get from a potential difference transacted over a certain distance, and then you gradually transform that into a kinetic energy by just adding rates of change. So we consider the rate of change as something moves over a trajectory, and then that gradually becomes kinetic energy. And in the same way, we can say that potential, a trust potential or trustworthiness that we assess in an agent from its history of promise keeping is turned into a kinetic response, which is how often we're going to sample the channel to make sure that it's, keeping its promises. And this now leads us on to the examples that I wanted to show you, which is what we can do with promise theory to explain how trust, in fact, leads to interactions, conflicts, and other shenanigans in the world of physics and sociology. So the first example I wanted to show is very quickly the Bell experiment in physics, which is the quantum entanglement experiment. And this is a very interesting experiment because the idea is that particles can exist in different states, spin states, spin up and spin down, and that when particles are created at a particular event, they're created in pairs, so with a spin up and a spin down, and that as they then move apart, these correlations between them are preserved. So particles come in pairs, say spin up and spin down. Here we call them Q and Q bar to point out that they're complementary. And as they move apart, they become separated by a distance, which means that eventually you wouldn't be able to send a signal from one to the other to maintain that correlation between them. Now, this is a matter of a certain amount of controversy in physics, whether or not there needs to be any kind of signal exchanged between them. Because when one particle is measured at a detector, d left or d right, the state that it measures immediately implies something about the state that must be measured by the other one. And people talk about the collapse of the wave function requiring faster than light communication because they're so far apart now that the signal will not be able to be transmitted in time. But promise theory gives us a way around this, because if we assume that if we assume that the particles being carried along are not labeled by simple scalar labels like up or down, but are in fact related to internal processes, and that these processes have a certain phase which is relatively correlated and so on, then in fact you don't need to have any signal transmitted between them, and you don't need to have any kind of collapse of a wave function, because all of the information is carried with the particle internally. And that means that we can solve the Bell problem exactly by simply equipping each entity as an agent with a kind of a sinus wave or a symbolic signal in the Shannon sense of up or down alphabetic characters. And that when we do this, we run an experiment over many times, and we can get a kind of a probability of figuring out which proportion of up and downs are measured relative to the detector in the usual quantum way. I'm running out of time here, so I apologize for being a bit fast. But here you can look at these signals. The parentheses on the right-hand side here are exactly what quantum mechanics predicts from the algebra. The other bold column is the measured result from a quantum, an agent experiment in which we're simulating the collapse of the measurement. And I can give you the code for this. You can run it for yourselves. And we see that within the boundaries of error, experimental error, these things match up exactly. So we don't need any kind of collapse or probability or any kind of mysterious shenanigans to explain the quantum phenomena if we assume that particles are actually agents and not simple billiard balls with labels on. Now, this of course doesn't mean to say that nature is like this, but it shows us that there is a way to take all of the mystery out of quantum mechanics, and I think that's a pretty important result in itself. For the last part, I want to talk about this chap, Robin Dunbar, who was a British psychologist, anthropologist, who predicted or came up with a hypothesis that the human brain is based on there's a social brain hypothesis, which says that the mass of our brain is related to the size of the group that we live in, or the size of the social groups that we're forced to live in. Because living in a group requires work. We need to help each other, talk to each other, pick nits out of each other's hair, and so on. This grooming between primates can be traced all the way back to the lower primates, monkeys, and so on. And if you plot a straight line through the cortical mass, the neocortical mass, and the size of the groups that they live in, typical community size, you find a straight line relationship, which tends to indicate that the functions of our brain relate to the size or the ability to perform work on each other's behalf to maintain the group, say in a swarm or a herd or a clique of monkeys or whatever. And this brings us back to trust as a form of energy, because if we think about the kinetic work involved in picking flies out of each other's hair, bugs, nits, and so on, grooming one another, or even just talking on the phone to one another, sending each other postcards or whatever it is that we do to maintain relationships, all of this requires work and leads to a kind of measure of our trustworthiness in society. So the extent to which we're willing to invest in a relationship would be related to the reliability of all of those past transactions, and so on. Now, the topology of the group is also important. So this brings us to the graph part. And if we think about a tribe with like an alpha male or somebody keeping the group together, and a collection of followers who are sort of following these, like an influencer monkey, followers who are following and interacting with this alpha. This gives us one structure versus a sort of completely ad hoc structure on the other side. And the ability to keep the group together or the amount of work we need to keep the group together now depends upon these structures. And we can try to work out what that energy cost might be, and to try to figure out what is the likelihood that a group would come together and stay together rather than, say, coming together and then falling apart. And again, hurrying because I'm running out of memory here, we can do it something like this. So the potential, or if we share the work between n-1 agents and sum all of that up, that leads to a kind of kinetic equivalent energy. Now, we don't know the units in which work is measured in this system, so we want to try to convert it into dimensionless quantities. And we can do that by introducing scales. For a velocity, we can have V0, and for the work done per agent, we can have angle brackets n, which is the average number of agents that we can work with. So this leads to a sort of energy of half nu squared, where nu is this quantity in the square root here, n-1 divided by the angle brackets n. And angle brackets n is the maximum amount of the maximum group size that we can cope with given a fixed energy budget. Right? So we can imagine grooming or processing, doing work on behalf of this group up to a maximum size of this. And so now, if we want to think about how groups form, we can look at group size. So the probability psi of having a certain group size, represented by this dimensionless variable based on n, is the probability of attaching to the group and the probability that we haven't detached from the group. And the rate of attachment is now nu to the half, or the square root of this nu variable. For the detachment rate, we can compute this using a kind of Shannon entropy. And it's always a kind of an exponential decay, a Boltzmann decay, because this is the maximum entropy distribution with a constant energy. So this is minimizing a Lagrangian of the entropy with two Lagrange multipliers, alpha making sure that the probabilities sum to 1, and beta guaranteeing that the energy is conserved. So the trust in this case is conserved. And this gives us an expression something like this, which we can plot and then compare to data from Wikipedia. Wikipedia is an interesting case because this is where people come together to collaborate on an article, writing an article. And we may think that they come together to help each other, and because they're good people and they want to help each other write something fantastic. But what actually happens, if you study it, is that somebody starts writing an article and then people start coming to see what's going on. Oh, I'm not sure about this, don't like this, we're going to fight you now, we're going to change what you wrote and make changes. And this leads to conflict. And eventually the groups accumulate to about 4 people, and then they collapse. And then they go away again, they come back later, they start all over again, and it all happens, and it grows to about an average of about 4 people. And so this graph on the right hand side shows the average group size, and the data underneath show the data from Wikipedia. The error bars show you the data, and then this curve fit is the theory based on promise theory here for what the group for what the curve going through the data show you what promise theory predicts it should be based on trust, given that the agents have a fixed energy budget and they don't want to invest too much work in one another if they don't feel that their promises are going to be kept. This is interesting in many ways because it relates also to brain waves. If we look at the frequency of sampling that the agents need to undertake in order to maintain this sort of energy budget group size, then this correlates quite well with the different states of attention in a brain. And if we multiply the group size by the brainwave frequency, we get this lovely 750 number to show that there is clearly some kind of connection between what's going on in the brain and what's going on in a group interaction, tending to indicate that Dunbar's hypothesis is, correct, or at least quite good. And of course, these are not exact numbers, but these are order of magnitude quantities averaged over different kind of trials. All right, I'm completely running out of memory here, so I have to stop. But if you'd like to read more about promise theory, there are these books. The first one is quite technical. The second one is sort of cozy reading, and the third one is also cozy reading with more of the details of this kind of more of the details that I've given in this talk. Okay, let's try and work with this. Okay,